Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 7.2. We're going to discuss the OpenCL device architecture. The objective of this lecture is for you to understand the OpenCL device architecture. OpenCL is a much lower level programming interface than what we have discussed in CUDA so far. The CUDA programming interface that we have been teaching is actually called Runtime API, and it's a higher level the interface that CUDA systems offer. And the compiler actually hides a lot of the architectural details from the programmers. There's a lower level programming interface in CUDA called Device API. And that level exposes a lot more of the hardware details to the users. And the OpenCL programming interface actually has a lot of equivalence to the CUDA device API. That's the reason why when we introduce OpenCL programming interface, we need to introduce more architectural level concepts so that you can understand the terminology used in the host code API functions. And also, you need to understand some of the memory models in order for you to understand how you can structure and program your kernels. So this picture shows the highest level of the hardware abstraction in OpenCL. OpenCL exposes CPUs, GPUs, and other accelerators as devices, which is exactly the same way that CUDA uses for GPUs. But here, OpenCL actually covers other types of computing devices, such as CPUs and FPGAs and so on. And each device contains one or more compute units. And these compute units in the CPU situation will be cores. In the GPU situation will be streaming multiprocessors. And in FPGAs, it will be could be soft cores or synthesized IP blocks. And each compute unit contains one or more of the SIMD, single instruction multiple data processing units, or PEs in this picture. And these PEs are equivalent to the streaming processors, or SPs, in the CUDA terminology. Here we show the architecture of a OpenCL device, and this is the architecture based on which you'll be writing OpenCL code. We have a compute device in OpenCL, and in fact, in an OpenCL program, you can have multiple compute devices, and each compute device consists of one or more compute units. And here we show n of these compute units, and each compute unit consists of multiples of these processing elements, or PEs, and each PE has a private memory, and this corresponds to the register variables in CUDA. And all the PEs in a particular compute unit can have shared access to local memory, and local memory corresponds to shared memory in CUDA. And all the compute units have access to a global constant memory data cache. And this is equivalent to the shared data cache in Fermi and Kepler processors in CUDA. And then eventually they have shared access to a global memory and constant memory, which is exactly the same arrangement as a CUDA global memory and constant memory. So this slide shows a summary of all the equivalents between OpenCL and CUDA. So we start with global memory. The host, which is the equivalent of CUDA equivalent, also as global memory. For global memory, the host code can do dynamic allocation, and this is equivalent to the CUDA malloc in the CUDA programming environment. So the host code will be doing all the dynamic allocation of memory for the kernels, and the host can also do read-write access by copying data into the global memory and copying data out of the global memory. And the device can access, or the kernel code running on the device can access the global memory through read-write access of all the by all the work items in all the work groups. And the memory appears as a large but slow memory, but it could be cached as we showed in the second level cache and even in the first level cache. So in OpenCL, the device does not allocate locations in the global memory. The constant memory is equivalent to the constant memory in CUDA, and the host can dynamically allocate constant memory. It can do read and write access. Mainly, the host code can actually do a initialization, which is a write access to the constant memory. So this constant memory really is relative to the device. So as far as the device is concerned, it can only do read-only access and by all the work items. And you can also statically allocate constant memory from the device code. And of course, this corresponds to the constant memory in CUDA terminology. Now, here is a little bit of a different terminology between the two interfaces. In OpenCL, we have local memory, which corresponds to the shared memory in CUDA. And for local memory in OpenCL, the host can do dynamic allocation. In fact, CUDA can also do dynamic allocation from the host code for shared memory. And that, remember, that's when we invoke the kernel, we can actually specify the portion that needs to be dynamically allocated in for the device. And but the host cannot do any read or write access to the shared local memory. And the local memory, as the case as in CUDA shared memory, only the kernel device kernel code can read or write into that local memory. So device can do static allocation, just like in the CUDA case, we can do static allocation of shared memory location, and the OpenCL kernel can do static allocation of arrays and variables in the local memory. And it's a shared read-write access by all the work items in the same work group. So whenever we have a variable declared in the local memory, there will be one version of that variable for each work group, just like there will be one version of shared memory variable for each CUDA thread block. And finally, we have private memory in OpenCL, and the private memory cannot be allocated or accessed by the host code, but it can be statically allocated and have read access by a single work item. So whenever we declare any variable as private memory variable in OpenCL, there will be one version per work item. And this is equivalent to the registers or the local memory in the CUDA terminology. So when we talk about OpenCL memory model, we need to start with the concept of OpenCL context. And OpenCL context is really the equivalent of a memory address space in the CPU or operating system concepts. So it contains one or more devices, and each OpenCL context can actually contain multiple of the OpenCL devices. And if multiple devices are declared in one OpenCL context, then these devices have shared access to the memory. And every OpenCL memory object is actually associated with a OpenCL context. So if we declare a variable in a particular OpenCL context, and then there are two OpenCL devices in the context, then both devices will be able to have shared access to that variable. So this concludes the introduction to OpenCL device architecture. And now we are going to be ready to introduce the OpenCL host code. And if you're interested in learning more about OpenCL device architecture, I'd like to recommend that you read section 14.3 of the textbook. Thank you.